So this is the first time. And so what I'm going to talk about is how we are trying to outsource our astrophysical data analysis to the real experts. And by that, I mean data scientists, as we start to move into the fields of machine learning where we are not experts. It might be a very good idea to get help from the experts. And we've come up with one particular mechanism to do that. So let's crack on. All right, so what I'm going to talk about is three sort of main things. I've got to give an introduction about gravitational waves and a little bit about me and what we currently do, what the state of the art is in terms of how we analyze our signals. And then I want to talk about the Kaggle challenge, and I'll explain what Kaggle is, but it's a data challenge that we set up in collaboration with this company called Kaggle. And I say it's the first challenge because we would like to do more. And I want to spend most of my time talking about that and the results, because then in the third part, I want to just talk about the results and what we learned about the challenge. And then I will summarize. And then I put that in red there to remind me to say, please interrupt me to ask any questions. If I'm using acronyms accidentally and you want things clarified, please shout out or type something in the chat. I'll try and keep an eye on the chat. And throughout, I've scattered lots of images. Not all are necessary to explain things, but I guess I should remind people that the plot on the right-hand side or behind me is the very first gravitational wave detection, GW 150914, very famous detection, showing the two signals detected in the LIGO and Hanford detectors. I also have a tendency to waffle and go too long in my talk, so I'm going to try and combat that today. So introduction, I've already had a very nice introduction about me, so I will take this very, very quickly. That is a picture of the University of Glasgow where I work. Sadly, I don't work in that nice building. I work behind that building in a slightly less attractive building. This is my history that Eric kindly went through briefly, but I'm born in the middle of the UK in 1979. Moved and grew up in Wales and did my undergraduate in Birmingham and my PhD in Birmingham, and that's where I found gravitational waves. That's what my PhD was on with Professor Alberto Vecchio. Then I came my first time to Glasgow, did a postdoc, really enjoyed Glasgow, but as you know, with postdocs you have to move. So then I went off to Germany to the Albert Einstein Institute to work in Bruce Allen's group. At the time I was working on continuous gravitational waves, but then when I moved to the next postdoc in Cardiff, I switched to the more popular and attractive compact binary coalescence, which are the signals that we have actually detected at this point in time. And then in 2013, I went back to Glasgow and I've stayed here ever since, and fortunately become a lecturer here. So that's sort of my argument as to why you should potentially trust what I'm about to say. And the next thing, I see a lot of familiar faces, or some familiar faces in the audience. So you will all know this, but I feel I have to do a brief introduction to gravitational waves for those who aren't familiar with it. And most people have probably seen a version of this plot this slide many times. So I'm not going to go into too much detail, but the effect of gravitational waves, as people may have seen before, is this weird stretching and squeezing of space-time, where if a gravitational wave were to be passing through the plane of your screen, it would have this effect in the transverse directions. And on the left-hand side, you have representative of the plus polarization state of this gravitational wave, sort of stretching up and across and oscillating with a certain characteristic frequency. And on the right-hand side, you have the cross polarization that's 45 degrees to this. And any particular gravitational wave will have its own particular frequency and its own particular combination of both of these effects inside that gravitational wave. Also labeled on here are the relative length and change in length of the various separation of points in this grid. These points are supposed to represent freely floating masses in space. And if I move my cursor so that I can stop, oh no, there we go. The equation at the bottom is just representing what we call strain, which is twice this ratio of the change in length to the length. And the thing to get across to people is that obviously this diagram is showing an H of order 0.1, but in reality, the kind of strains that we expect to see and that we have seen from the universe, the gravitational waves that are generated by some of the most violent things in the universe, or energetic things, by the time they arrive at us, the strain is incredibly tiny, at 10 to the minus 21, and so we need some of the most sensitive instruments in the world to detect those gravitational waves. So, there we go. So the kinds of signals that we're actually looking for, we've typically broken those into 4 categories. Compact binary coalescence being the top one. I'm going to talk about that more in the next couple of slides, but I did just want to mention that we also search for unmodeled transient bursts of gravitational waves, things that sort of go bump in the universe that we weren't planning, we don't have a model for. Then continuous gravitational waves, which is just a constant emission of gravitational waves, a very low amplitude and usually at a sort of very nearly constant frequency. And then we also have the stochastic background of gravitational waves, noise from the universe in various forms. But what I'm going to talk about is the famous one, compact binary coalescence, the one that we've actually, where we've actually already detected signals. And here we are. Here is it's great that people make these animations because you can just plug them straight into your presentations and it tells the whole story. So if anybody hasn't seen this kind of thing before, and I doubt it, this is just a numerical simulation in full general relativity from the Mallorca group, I think. I should double check. And you're seeing 2 black holes orbiting each other with, I think they look like they have slightly different masses. They have arrows going through them to indicate their spin vectors, and then at the end they merge. And in the bottom there, you're seeing the gravitational waveform that you would expect to see from that. So I'll go back to there. So it's not really showing the full gravitational waveform, but again, just for people, for their knowledge, the kind of signals we expect to get are time series signals in our detectors. We don't get images, not like a normal telescope. We are measuring, it's kind of like a microphone listening to the universe. And what we end up getting is waveforms in strain that look very much like that waveform in red at the bottom. Unfortunately, it's only half of it shown at the moment, but I've got other plots of it later on. There we go. And this plot is representative of the current state of our detections, the LIGO-Virgo-Calgary collaboration, and the sheer numbers of things we've detected since 2015. So the very famous one was GW 150914, which is somewhere in there, represented as two blue masses that merged to make a heavier mass. But since that time in September 2015, we've detected about 90 of these events in the universe. And you can see their range in masses on the left-hand side axis, ranging from the bulk of them are in the tens of solar masses that merge into close to 100 solar masses. But we have seen a couple of binary neutron star mergers as well. So these are not black holes merging together. These are neutron stars weighing about 1.5 solar masses each and merging into what we think are low mass black holes. And we've also seen some binary neutron, black hole neutron star mergers where it's been a black hole and a neutron star together that have then merged together into a larger black hole. So this is the culmination of the LIGO-Virgo science runs since 2015, and I say we just completed it. It's maybe a year ago. I can't remember the dates now. Time has no meaning in COVID times, it seems. But the last run was the 03B run, the third science run of the advanced detectors. Prior to that was the 03A and 02 and 01, which has given us all of these events to study. So I want to say a little bit about how we currently find our signals in our data. And so there's another representation of the same famous signal, GW 150914, the raw, semi-raw data in the top 2 panels showing the noisy signal in both the Hanford and the LIGO detectors. So how do we go about finding these in our data? when we get this time series being output from our gravitational wave detectors. So another animation that's useful, hopefully it will work if I press this button. There we go. So what you're seeing on the left-hand side is two time series. In the lower time series, you can see gravitational wave data in black, noisy gravitational wave data, and a template in sort of pink. And in the top panel, you're seeing the correlation of the template with the data. And this is sort of the essence of matched filtering. We're taking a filter, the pink known predicted signal from general relativity. I'll play that again. So that we've worked out what the waveform should look like for a particular pair of masses, and then you're correlating with the data. And if you look at the top panel, we're getting some noisy SNR measurements, signal-to-noise ratio, as our statistic. And then at some point, there we go, we get a big spike, because at that particular point, the template matched very well with the data. So it's implying that in the data there was a signal with a very similar waveform, and it's giving us a big output statistic. So I will play that, but then pause it. Try and get rid of that advertisement. And then on the right-hand side, what I'm showing is the fact that we don't know what masses and what signal is going to arrive at which time. So what we have to do is make a thing called a template bank, which is a whole big collection of different waveforms that could arrive. And those waveforms are typically characterized by their component masses. So if you change the component masses in the binary system, it's going to make a slightly different waveform. And if you see on the top, so what we're plotting here is mass 1, the heavier mass, versus M2. I'm sorry, it's covered up the axis label there. In the upper corner of this plane, it's in log scale, so these are quite heavy masses, tens of solar masses. You tend to get short, low frequency type gravitational waveforms, but with a relatively high amplitude. Heavier mass gives you a stronger signal, but it also gives you a lower frequency evolution of that signal. Whereas down in the left-hand corner there in the green, you're looking at low masses, potentially binary neutron stars actually rather than black holes, and they're going to have a higher characteristic frequency, and they're going to be longer waveforms that last many tens of seconds in our detectors. But generally have lower amplitude overall, but higher frequency content. So what we tend to have to do in practice is generate this bank of templates, run all of those templates against the data, and try and find instances where the data is giving us a high correlation with those statistics. That then indicates when the event happened. It also indicates the potential masses that are there, and then that event is tagged as a candidate event, and it's passed on to further data analysis to do more rigorous studies of that piece of data and that signal. So next thing to talk about very briefly is our own efforts in the gravitational wave fields in terms of machine learning. So everything I've talked about till now is sort of classical data analysis and what we do to find these signals buried in noise in our time series. But in the past five or so years, people have tried to put effort into using these newfangled machine learning techniques. That previous slide was supposed to represent the bandwagon that we were all jumping on to get these new fancy techniques to apply to our data. And so I wanted to have a slide to just say that it's really growing. The amount of literature on people applying machine learning techniques to gravitational waves is growing. There's a link there to a nice review paper on this, which already is out of date. It's 2 years old, and there's lots of stuff that's happened in the last 2 years. So lots and lots of problems have had machine learning applied to them within the gravitational wave data analysis field, and a lot of the available tools in machine learning have been applied to these problems. Ranging from your basic classification algorithms to your sort of more fancy probabilistic modeling and normalizing flows and generative adversarial networks. Lots and lots of different things been applied. And the most recent work, the plots on the right hand side are sort of representing what I think is the most exciting things happening is very rapid Bayesian parameter estimation that's gone on, and it's blatant self promotion there. That's a paper from my student there, but there are some other very, very good, if not better, work out there in the literature on this same thing. The one thing I was saying here at the bottom here is that so CBC searches were one of the first things to be looked at in terms of the astrophysical side of using machine learning for our data analysis. However, there's still no serious machine learning pipeline that we're using in our collaboration. We're still using the tried and trusted old thing. So go on.
What does CBC mean?
Sorry, thank you. Compact binary coalescence. That's the problem with having too many acronyms. Thank you for asking that. That is this compact binaries. That's the two black holes or the neutron stars in a binary system going around each other and merging into our signal. So that's what I mean by CBC. Hope that's clear. But there is still no serious machine learning search for compact binary coalescence. There are people working on it, but it hasn't sort of appeared yet. There's been papers, we've had papers on how you can do this. And the last thing I want to say, which is relevant to this, more relevant to this talk, is that we're astrophysicists. We mess around, we learn our data analysis, and then we have to learn our machine learning ourselves, being self-taught. And there is a whole host of people that are the real experts, and that's the whole point of this talk, which is what I want to get onto, hopefully, very soon. Yeah, there we go. All right, I've timed it quite well. So given the fact that we know what we're doing in terms of searching for gravitational waves, but we are trying to dip our feet into the water of how to do these more advanced data science, machine learning type approaches. This is what brings us to this first Kaggle challenge. So first of all, Kaggle, it's a very strange word. What does it actually mean? It's the name of a company. This is a representation of what is on their website. It's not their front-facing page, but it's their competitions page. So Kaggle, I'm sure they would define this differently themselves, but they're a company with an online presence that sort of hosts and creates an environment for data scientists to communicate and to share ideas and potentially predominantly enter into competitions, data analysis competitions, data science competitions. And those competitions come from the general public. They also come from Kaggle themselves, but more often than not, my understanding is that both companies and academia provide challenges and sort of curate data science challenges together, working with the people in Kaggle to give challenges that the Kaggle members can apply themselves to for both for fun, for money in some cases, and I'll talk about that later, but also just for kudos, just for the Kaggle credits, which are very good and very well respected sort of currency in the data science community. So right there, this is a page I think I took a week or two ago when I started writing this talk. You can see there's a Kaggle challenge on the Titanic, house prices, a digit recognizer, and that's just the top 3 there that were on the website. There's many challenges that you can get stuck into. So what was our challenge? What did we try and do? So there's the top banner that you would see if you clicked on our challenge page, if you went to Kaggle and found the challenge. The challenge is now complete, but it's still there to view all the information. It's called G2Net, gravitational wave detection, because G2Net, I'm part of a European cost action, which is a group of people we've obtained funding from European funding agency to fund networking in gravitational waves and in geoscience as well. So they were behind this. This was all done as part of that project. And you can see this ended 6 months ago. It's related, the cost action is related to the European Gravitational Waves Observatory, EGO. And there's a number that I'll come back to. 1,200 teams of data scientists attempted our project. So we were very surprised at how popular this was. And again, I'll talk about that later on. So what did we actually ask people to do in this challenge? Here is essentially, it's a very bad slide. You should never do a slide like this with just lots of text, but I wanted to sort of get across the fact that that is all we told people. You know, you go and do a PhD in gravitational wave data analysis and you get told a lot more than that, right? You have to read many, many textbooks and learn how to do lots of things. But this is all we told people. And we were encouraged by Kaggle to not tell them too much. We don't want to contaminate people with our own existing ideas. We want them to look at the data challenge in its purest form and come up with new and interesting ways that we hadn't thought about for how to analyze our data. So I'll read this a little bit. So the highlighted bits are the most important bits. In this competition, people are provided with a training set of time series data containing simulated gravitational wave measurements from a network of 3 gravitational wave interferometers, the 2 American interferometers and the French-Italian detector Virgo. Each time series contains either detector noise or detector noise plus a simulated gravitational wave signal. And the task is to identify when a signal is present in the data. So this is a basic classification problem, trivial to many data scientists and machine learning experts. The difficulty comes in the fact that our signals are very, very weak in our data. And so that was their challenge, to dig out the signals in the data and try and find more than their competitors had found. We tell them a little bit about the parameters of how we parameterize our black holes. These are black hole signals, compact binary coalescences, which are parameterized by 15 different physical quantities, the masses of the black holes, where they are on the sky, how far away, and various other parameters. But we didn't tell them what those parameters were. We just told them in training data whether or not there was a signal or not in the data. And in terms of practicalities, each data sample had 3 time series, 1 for each of the 3 detectors, which spanned 2 seconds of data sampled at 2 kilohertz. So in total, you're getting 12,000 numbers representing a single item of data that we're giving to people. We also then had this final paragraph about signal to noise ratio, because we wanted to give people just a general hint about what we're looking for, but not too much of a hint about how strong the signals are that we're putting in. Because if you open up the data, I'll show you in a second, you don't actually see the signals. You can't see them. So people were a bit confused initially. This data is labeled as having a signal, but they couldn't see it. And that's because they really are buried deep in the noise. And here we are. So here is a representation of the data that we gave them. And it's this data behind me on the right-hand side is a representation of one of the pieces of data that we gave them, these 3 time series. Now, a lot of people looked at this who were not familiar with gravitational waves and said, oh, that looks like the signal. It's oscillating. It looks like a gravitational wave signal. That is not the gravitational wave signal you're seeing on the right-hand side. That is just the noise. It's completely dominated by noise here, especially the low frequency noise. All those oscillations you're seeing are the low frequency noise, because we gave people unwhitened data, unpreprocessed data. So it had essentially raw gravitational wave noise. This is simulated, lovely, nice gravitational wave noise, not nasty noise that we have in our real detectors sometimes. But still, you can't see the signal there. And if you look on the left-hand side, this is an example of some of the signals that we injected into the data. And hopefully they do remind you of some of the plots I'd shown earlier, where you have this in-spiraling, oscillating waveform that gets higher frequency, higher amplitude, and then sort of ends very abruptly and then goes to 0. And so the one thing to keep your eye on is the left-hand side is the y-axis scales. The scale on the left-hand side is 10 to the minus 22, and the scale on the right-hand side is 10 to the minus 20. So the right-hand side does contain a signal, but it is 100 times lower amplitude than that data there. And that is because of this low frequency noise there. Now, in our analysis that we do classically, what we initially do is we whiten the data. We essentially suppress the low frequency noise, which enables you to see the signal a little bit better, but not always in the data. But we didn't want to do that for these contestants. We wanted to give them raw things to see what they came up with as an approach to this problem. So the next thing we had to decide is, and this was hidden from competitors, so all the information now was not told to competitors in the competition. So we generated noise from the O4 advanced interferometer power spectral densities. So that is the predicted sensitivity of the 4th observing run of our advanced detectors, which is going to start later on this year actually. But we have predictions for the noise levels that we are expecting. So we put that into our calculations. We also used astrophysically sampled distributions of our astrophysical parameters, so where the gravitational waves were on the sky, how far away they were, the masses the distributions of masses we expected, things like that. And then we left ourselves with one tunable parameter, which was the redshift cut. Redshift is kind of like distance. It's related to distance. And what we did, we said we were going to tune the maximum redshift of the signals we're going to inject, which controlled how strong the signals are. If a signal is very close to us in redshift, it will have a very high amplitude and a very high signal to noise ratio. Whereas if it's very far away, it will have a low signal to noise ratio. So we said, we tuned it to have a redshift cut of 0.5. So there were no signals generated beyond that point. And that resulted in this distribution on the right-hand side of our training data that we generated. And so it peaks around a network SNR of 6 or 7, and it has long tails in the positive direction beyond the extent of this plot, actually. And it has a tail that goes down to close to 0 as well. Because what we wanted to do, we wanted to give a chance for the competitors to do better than we can do. So we wanted to give them signals that we knew we couldn't detect. And we also wanted to give them signals that we knew we could definitely detect, because we want to, again, there's two sides to this challenge. One side is to get the best data analysis people involved in this to help us out, but it's also an outreach tool. And we want people to be engaged with this problem, so we couldn't make it too hard. So we needed people to be able to find some signals and say, yeah, I'm doing gravitational wave data analysis. And I think we ended up tuning this very, very well, probably more by luck than judgment, but it worked out quite well. And I've got this red area in the middle just to sort of represent this sort of an uncertain region where we weren't sure whether things would be detectable or not. That's sort of the boundary where we currently live with our classical tools. I should say as well, our classical tools are quite well known to be near optimal at this point. So machine learning isn't going to do groundbreakingly better than classical tools, but it does have some benefits, which I'll hopefully talk about later. So we took a long time tuning this distribution, going back and forth, and that was the most important thing we spent time on, because those points I was discussing before. Yes, yes.
What does it mean near optimal? So where does this come from?
So matched filtering itself is known as optimal in the via the Neyman-Pearson criterion for a single matched filter template. So it's optimal in terms of the highest detection probability at a fixed false alarm rate, if that makes sense to you. And matched filtering is known to be optimal in that case. However, that's only true for a single template and not when you have a big bank of templates and you're searching over those templates. It's also not true in non-Gaussian noise, which we also have. So there is room for improvement over matched filtering.
Okay, thanks.
Yeah. I see Natalia has a hand up as well.
Hi, Chris. Sorry for my ignorance, but the redshift of 0.5, you limited it not to be higher than that or lower?
No, good point. Good point. Not to be higher than that. So,
okay, yeah. And what is the reason then? So, I mean, why don't you go smoothly to the signals that you know you're not going to detect, or just to limit the volume, so to say, of the data?
Well, limiting the redshift is the same as limiting the physical volume around a universe.
Okay, so like you limited a bit like further than you know your detectability is, right?
Yeah, so all the signals on the left-hand side of this distribution are either at high redshift and therefore high distance, or they have low mass, or a combination of the two. So remember, low mass gives you low amplitude as well. So we wanted to keep our life simple and boil it down to one parameter we could tune to change this distribution. And so it just moved everything to the right if we lowered the redshift cut, and it moved everything to the left if we increased it. So we just chose that as a nice level.
Okay, and for the masses, you just chose sort of.
It was an astrophysical distribution motivated by what has been seen in the first couple of LIGO runs.
Okay. Okay. Thank you.
No problem. Okay. Final point on this thing is if anybody else is wanting to come up with a Kaggle challenge, you've got to be aware Kagglers are both devious. They're very, very smart, but they're also devious, and they will cheat in inverted commas if they can. And it's within the rules to cheat. If you can find a way to reverse engineer the problem, then you can do that, and it kind of negates the challenge in a sense. So there's lots of care goes on in checking that your data doesn't contain any clues, doesn't contain any residual sort of effects that you've put in when adding signals, which give the data analysts a hint of what is in there in the testing data. So you've got to be very, very careful. And I mention this because we could have used real data, because LIGO and Virgo data is publicly available, some of the old data, and we could have used that data, which is more representative of real data, to simulate our signals in. But it was told to us that Kagglers could go and find that real data and subtract it from your data, and then just get the signals back exactly, and therefore cheat. So you've got to be very careful with these things. Yeah, anyway, I'll move on. So another aspect is, here's just some stats. We generated 500,000 items of training data and gave that to them. They're labeled with the 0 or 1 for the two classes. And we had testing data of 220,000 items. You might ask, why do we have so many testing data? And the reason for that is we really needed to get the Kagglers to probe a very low false alarm rate. And so on the right-hand side is an ROC curve, receiver operator characteristic curve, or a diagram of one. And what we're hoping for is you can take somebody's classified data. If somebody's got some test data and classified it for you, you can convert that into a curve on this plot, which represents the number of times that you're going to guess the wrong answer versus the number of times you're going to guess the correct answer. And you want your curve to be as high and to the left as possible. And that perfect classifier defines that on the top left. And if you had a completely random classifier, it will be a diagonal line. And what we ended up doing in conjunction with Kaggle is using a metric, which was the area under the ROC curve. Now, this is not standard to gravitational wave analysis. We don't usually ask to maximize the area under the curve. Obviously, maximizing the area, you will get the maximum area if you are further and higher to the left of this curve. And it's a standard metric node that's used in Kaggle and data science, but not to us. So we had to scratch our heads a little bit about this. And the reason we have that is because typically we don't ask for the area under the curve. We define a false positive rate, a very low one, and we ask, can you make the curve as high as you can at that particular single value, rather than maximize it for all values. So this is I mention this because when you're making a challenge, you have to choose a metric to decide who wins the challenge. And so in this case, it was the area under the curve. And you'll see the results later on. Unfortunately, we were okay in terms of using that as a metric. Okay, so the process. So now, sort of away from the science, but more about the sort of process we went through with Kaggle, the human aspect, really. So when we got involved with Kaggle, we were put together with those two very nice people listed there, Maggie and Walter. So Maggie was our sort of customer success person, whatever that means in the Kaggle infrastructure, but she was our point of contact, and she was very, very helpful in helping us sort of understand the contract, understand how we put together our website, our web pages on their website, and describing how we communicate with Kagglers and how much information we should give them and how much we shouldn't, things like that. Walter was the data scientist who sort of helped us sort of curate the data and package it up to put on the Kaggle site. He's a previous Kaggle expert. He used to do the challenges, and then he joined the other side, and now he works for them. And then below there, we've got the main guy, Michael Williams, a PhD student here at Glasgow, who did all of the hard work in terms of generating the data and simulating everything. And then we were working together there with Christopher Sarafa and Eleanor Cuoco, who were part of this G2Net cost action, and it was Christopher's idea really to do the Kaggle challenge in the first place. And on the right-hand side, that weird table, this is a table sort of representing, it's actually showing the winners of our challenge, but it's representing the fact that there's thousands of people involved on the other side, the Kaggle competitors. So there was 1,200 teams took part in this, which I don't know how many individuals that was, but you can see here when it says members, each team can have a number of people in it. So there's probably of order, 5,000 or so people that took part in this challenge. The timeline for this, for those who are interested, July 2020 was when we first started having conversations with Kaggle, and we were holding monthly meetings after that point with them, going away and making the data and thinking about the challenge we wanted to set. In October, we sent them our first set of trial data for Walter to have a go at and see if he could cheat. Essentially, he wants to check if people can cheat on the data set. In January, we started drafting the documentation, and then in early 2021, we didn't even ask them, but Google gave us $15,000 as prize money to give away for this challenge. We were not expecting to have a prize, a financial prize, but we ended up with a financial prize to give away to people. So that, I'll talk about that later on if I get there. We decided to the metric, we signed the contract, and then the competition was launched in June, end of June 2021, and it was a 3-month-long competition. I'm looking at the time. I want to sort of push on. One thing during the challenge, we didn't really have to do much other than sort of monitor the chat, and there was thousands and thousands of messages between Kagglers, but it was between them and not to us. Very rarely did they want anything from us. They just wanted to chat amongst themselves about how they were doing this competition. So the results and the winners, and the plot on the right-hand side is there to sort of represent the other aspect other than cash. So whilst there was $6,000 for the top prize, $5,000 for second and $4,000 for third, they weren't that interested in that money so much. It was more about these levels of kudos and where you get in Kaggle. And you start off as a novice and you can elevate yourself all the way up to a grandmaster, depending on how well you do in these challenges. And here they are. Here are our winners, a team of 2. And we have a grandmaster and a master, Selim and Dennis. And there's their information. I mean, they do this for a living, basically. They are computer scientists, data scientists, working at various startups and companies. I think the places that they've worked changed during the length of the competition. Dennis is doing a PhD in computer science, or he was doing at the time, in parallel to everything. Things that attracted them to the competition, it was an unusual competition topic. You don't often get astrophysics challenges, apparently. And also for Dennis, he was just attracted by the digital signal processing aspect of this. And they both did this kind of as a hobby, although a 2 to 4 hour daily hobby for 1.5 months, I'm just realizing is quite a hobby. And they ended up with the $6,000, which is asking them afterwards, this was not a motivation for them to win the thing. All that will do is buy them another GPU for their next analysis. And they already have loads. So that wasn't a motivation. It was just the pure interest of doing this challenge. And for those people who are interested in the actual architecture of what and the approach that they took to this, it's sort of outlined here. Nearly all the top challenges had a very similar type of architecture where we have our time series, and it was seen, a lot of them decided that the time series needed to be turned into a 2D map. And we often think of in terms of spectrograms, time frequency maps for our gravitational wave analysis, but they were using 1D convolutional neural networks to convert each time series from each detector into basically a 2D image. And you can see here in this flat layer here, after the conv 1D encoders, they called them, you end up with 3 channels, 1 for each detector, and 128 feature space by 128 channels, which they said sort of was very similar to a spectrogram, but not quite. And this is a learned quantity. It's not just doing a spectrogram of the data. It's learning how to represent the data in this sort of compressed form. And then now they've got it into a standard form. They just throw this into a standard pre-trained network, a ResNet 34, and output the results and train this thing. So a lot of the effort was gone into how to do pre-processing, what they call the front end. Again, this terminology is not sort of standard to me, at least in the gravitational wave data analysis. And this is representative in general to what a lot of the top, the winners, not the winners, but the people who came in the top 100 sort of ended up applying. The one thing that sets the winners apart from everybody else, though, was they did reverse engineer the problem, but not in a cheating way. They realized that they could enhance their analysis if they had extra information, and the extra information was the parameters of the signals. If they had access to the parameters of the signals as well and asked the network to predict the parameters, it helped the network actually find signals. But they weren't given the parameters. So they reverse engineered the problem, and they basically reinvented matched filtering, ran matched filtering on the training data to find out the parameters of the signals. And then they attached those, then they also used our existing PyCBC codes, our general codes that we use to make signals and do our matched filtering. And they used that to generate new signals using the same distribution of parameters that we had, but we hadn't told them, but they'd gone and worked it out by finding the signals. I was just amazed by the ingenuity they'd used, which in the end allowed them to make infinite amounts of training data. They weren't limited by the 500,000 pieces of training data that we'd given everybody. So that's what set them apart. And you'll see in a second, if I get to it, the results, comparing the results. There it is. In terms of an ROC curve, look at the left-hand side plot. This is in linear space, the same sort of diagram I showed before. You want the curves to be as high and to the left as possible to get the highest sensitivity. And you can see the area under the curve statistics that the winners, the second place and the third place got. They're indistinguishable on that plot. But if you look on the right-hand side in log space, you can see where the big change was. It was the winners were able to continue to get high detection rates at very low false alarm rates. And that's mostly because they were able to generate infinite amount, not essentially infinite, but they had so much more data to train on than the other teams. And that was what we were really worried about, is whether the metric, the area under the curve, the winners in that metric would still represent getting high detection rates at low false alarm rates, which is what we're really obsessed with in our collaboration. I see that Natalia has a hand up.
Hi. So about this last thing that you explained, I have two questions. So one is, so in principle, if you imagine you would give them not the training data that is limited by a number of samples that you have, but the generator, so that they can generate the data themselves. So all of them then would sort of perform similarly, right?
I think so, although it's a bit of a guess, but that's what the winners said, was that pushed them over the edge, to say.
But I didn't quite understand how they reverse engineered the problem. So they sort of like denoise the data to get the templates, and then how did they find the sort of signal?
So what they wanted to do, they needed to know the distribution, the astrophysical distributions that we simulated, all that stuff I talked about before with the redshift cut and everything. They didn't have access to that, and they needed that in order to generate training data that was similar. So they basically ran matched filtering on all the signals in training data, estimated their parameters using matched filtering, used that to construct distributions on the masses and the distances and the other parameters, and then generated their own training data with those same prior distributions.
They found somewhere the templates, right?
Yes, yeah.
Okay,
yeah.
I see. Okay.
Okay. Oh, sorry. Next plot is efficiency. So if you fix particular values of false alarm rate, and then you plot the detection efficiency, the true alarm probability as a function of the SNR of the signal, then you get the left-hand plot for the winners, and this is at different false alarm rate thresholds. So the very lowest false alarm rate thresholds are getting towards the more realistic ones. So the dashed red line is roughly where our sensitivity is around SNR 10. You start to detect everything above SNR 10. On the right-hand side is a plot from a paper that we had in 2018, where we applied matched filtering and compared it to our version of machine learning. And the matched filtering plots are the other sort of greeny blue curves on the right-hand side. Now, it's not a fair comparison because they're different data sets. So this is a rough comparison. We're working on the proper comparison at the moment, but so we haven't got that final result for you. And what our final result should be is we run correct matched filtering on the training data from the Kaggle challenge, so we can have a fair comparison. So this is just a rough comparison. And if I scale the plots and plot them over the top of each other, what you're looking for there is the sort of purpley lines, no, not the purpley lines, the sort of bluey green lines compared to the red dashed lines where my mouse is. They're close, and it seems to imply that match filtering is still doing better, but I think that's not true at all. This is not a fair comparison. They're different sets of data. So we do need to dig into this a bit more to find out really how they compare. So the jury is out. I don't have a result for you, sorry, Eric, about which one is better, but they're going to be close. They're going to be close. And then in the final couple of minutes, we were so sort of pleased with the reception and how people engage with this challenge. And so were Kaggle. Kaggle told us they were really impressed with everything and how people received it. We're going to try and do another one, and this time we want to do a problem that is actually a real problem, one that we cannot solve in gravitational waves at the moment, which is the problem of continuous gravitational waves. So this goes back to what I was doing my PhD in, so it's sort of full circle. And I won't go into the details, I don't have too much time, but it's a harder challenge. The continuous gravitational wave community has not detected gravitational waves yet. That's not their fault. They just might not be that many of them out there, and they might be incredibly weak. We know they are incredibly weak, but they might be, it depends how incredibly weak they are, which is going to determine when we finally detect them. But our analyses for continuous gravitational waves are computationally limited. So we have to make sacrifices in how we do the data analysis, and we lose sensitivity based on limited computational resources. I say limited, I'm talking about 1,000 node clusters here running for 6 months. So we're using a lot of computing power, but it's still, we're throwing away sensitivity. So the next challenge we're making is a continuous gravitational wave challenge, and we hope we'll be launching that in a few months. And then just to summarize, there's the sort of the outline on the right-hand side to remind you what we talked about. But the things I've learned is that there's a vast wealth of untapped knowledge and skill that we can harness to enhance our scientific impact, especially if we're getting into this machine learning business and we're kind of amateurs. I mean, I certainly am an amateur, and I'm just learning from all the young people around me that are coming out with these new ideas. But there is a whole community we can tap, and they are really interested. So there's a two-way situation. It's not just us taking from them. They really enjoy it, and they do it for fun, and not necessarily for the cash. We're currently behind. That gap is going to get narrower. We're going to get better, especially like my PhD students know machine learning very well already, and so it's going to become commonplace analysis that we'll be using. And in terms of the CBC challenge, this first challenge, we plan to incorporate what we've learned in future CBC searches that we're developing right now. And I'm really excited about the next one about continuous waves, because that's one where I've got so much hope that the problem is going to be found outside our community. So I'm really looking forward to that. And that's everything. So thank you very much for your time.
Thank you very much, Chris. That was very interesting. So I see already hands up and question in the chat. So I'll start with Antoine's question. I guess Shall I? Do you want to go ahead and Antoine and ask the question yourself, or should I repeat?
Yeah, I'm just asking thank you very, it's a very nice talk and very interesting. Are you planning to use real data for the continuous gravitational wave, or you are doing with simulated data?
It's going to be real data. That's our plan. It's not.
Cool.
It's not definitive, because that was one of the comments and the feedback we got about the first challenge. Not necessarily from the Kaglers, but from the gravitational wave community. Of using Gaussian noise is so last decade. We really not need to challenge look at the problems where there is non-Gaussianity and CW signals. The vast majority of bands, because you look in narrow bands, they are very Gaussian, but there is a large fraction that have line artifacts and things and wandering lines that need to be addressed in a real data analysis problem. So we hope to use O3A or O3B data, which is publicly available, and simulate into that, but we will have to address the challenges of cheating and reverse engineering, and we've got some ideas about how to do that.
Thanks.
Okay. So I see 3 hands up. I'm not sure what's the order, but I'll use my screen here. The first is Temis.
Yeah, thank you very much for this inspiring talk. With regards to the different kinds of gravitational waves that you mentioned at the beginning, so is the CBC the easiest one to attack? So how do they compare in terms of complexity and of complexity to detect?
Right, that's a good question. So it was a combination of simplicity, but also the sociology as to why CBC was the first to be attacked, because CBC is so popular. That's where we've detected signals. It also turns out to be a relatively straightforward challenge. I mean, even we were able to do it. We had our paper, and a bunch of people had papers out in 2017, 2018 about how to do this basic binary classification with convolutional neural networks. The burst side of things, I think, is really interesting to look into, because that's really where machine learning can use its other string, which is the unmodeled nature and the fact that we don't have to tell it what it's looking for if you're using the right machine learning algorithm. And also the CW one is going to be very much like the CBC. It's a signal in noise. But that classically is a harder problem, because the parameter space, the parameter space is so vast for CW. You're looking for a needle in 1,000 haystacks, whereas for a CBC signal, it's just maybe half a haystack that you're looking for it in. Stochastic, I think, is a solved problem, but other people may disagree with me. I don't work in stochastic, but I know the LIGO collaboration has a sort of standard approach for that. I don't think I'm missing out any, but I think it was a mixture of, it was relatively easy and also popular to look at CBC.
Okay, thank you.
Okay, the second in the list is Yvonne.
Hi, thanks for the very interesting talk. Thanks very much. It's another perspective on machine learning, another window, which is possibly opening. I have a question on the fact, for instance, if you're going to use these algorithms which are being developed by the Kaglers, how are you going to acknowledge this contribution in the papers, for instance? Is it Kaggle or is it themselves? How does it work?
Right. That's a good question, and we addressed this when the competition ended. We had the meetings with the first 3 place people, winners meetings, and it's sort of standard in Kaggle. And there's one of the questions I asked, like, would you be happy in us publishing with you guys as authors? And we have a big paper describing the top 3 winners, and we've got everybody that's been listed here in this talk, including the winners. And they were very surprised that anybody would care. And they said, yeah, fine, we don't care. So they didn't feel, I got the sense of not great, ownership, this is mine, you can't have it. They were very open to discuss stuff. And if you go on the Kaggle website and you look at the forums, everybody's very, very sort of sharing with all their approaches. They'll keep their best approach for themselves to win the challenge, but they're quite happy to share their notebooks and things like that. In terms of Kaggle being acknowledged, I'd have to ask them. I'd be very happy to acknowledge them because they've been so helpful.
But I was thinking, for instance, if you do a huge discovery,
Right.
I mean, very huge, then maybe they will be happy to be acknowledged for that. I don't know. I don't know.
I would be incredibly happy, and hopefully I continue this openness of saying that it's really them that are doing the work, and we're trying to learn from them.
Sorry, I have another question, also on Kaggle itself. Is it a free service in the sense that anybody can use Kaggle, and how does it work? Or do you have to pay something? I don't know.
You can join. I think it's just giving your email address or usual signing up to something. It's free, and then you can enter these competitions and submit your results. It's totally free. I tried to do it years ago, but then my work became too busy.
Yeah, no, but I mean from the proposer side. So I think
yes. That's a good question. They for this new challenge we're doing, they accidentally sent us the wrong contract, the non-academic contract last week, and I saw how much it would have cost if we were a business.
Could you tell us?
Is it still being recorded?
Yes.
Yes, it is. Maybe we can switch this.
We can stop the recording.
Off. Yes.
No, I can say tens of thousands of dollars.
Whereas for academics,
free.
Okay.
Free. We were very relieved when they said that's the wrong contract. So yeah, tens approaching the next order of magnitude. If you were a company and you wanted their expertise in hosting this for you. So in that sense, we're getting a lot of value for free as academics.
Okay. Thanks.
Very good. The next in the list is Natalia.
Hi, thank you very much for the talk. I have a couple of questions. So first, you said that you defined the SNR, and did you kind of define what exactly SNR means? Like, did they use that? Like, why?
No. So again, that's riding that line of not telling them too much information. We did want to use the phrase SNR in that first description page, and specifically say integrated SNR, because a lot of people get confused with integrated versus instantaneous. But in the end, we needn't have said that, to be honest. I think we were just being a bit too safe. In the end, majority of Kagglers didn't use that. They weren't given that. So it wasn't part of their analysis.
And okay, and so the other one, so they all of them, you say most of them use these pre-trained networks that they then retrain to your particular problem. So they didn't kind of come up with their own stuff.
Yeah, so the backends that we used, again, I've only looked at the top 3 winners in detail. They were the ones who were obliged to present us with their codes. The other people don't have to. And so there's a lot of stuff to dig through, so it's taking a lot of time. But their sort of overall description, all 3 of them. Pardon me. Sorry. All 3 of the top winners. Oh my God, my voice is gone.
Sorry.
Too much talking. Had this front end, which was to pre-process the data into some kind of image, followed by a back end, which was, whether or not it was pre-trained, maybe I misspoke, it was certainly pre-designed, a standard ResNet 34 network. Yeah.
And the last question about these distributions, I still don't understand exactly. So first, does it mean that they reverse engineered your physical distribution of the parameters?
Yes.
Or it just mattered? So then it means that it really matters to bring your detection to lower SNRs. It really matters that you know astrophysical distribution well, right? So if you make a wrong astrophysical distribution, but you create millions of waveforms, it still will be worse.
Well, all right. So just to be clear, the training set and the testing set had the same astrophysical distribution. So all competitors had access to the correct one. But for the winners to make 10 times, 100 times more training data, they just needed a way to work out what that distribution was. So part of what you're saying is true.
So even if they would have just created waveforms with a noise, but they would know, they would, let's say, sample uniformly know the parameters,
Yeah.
that wouldn't help them so much. Ah, okay,
We
that's
don't,
interesting.
that's what they imply to us by the fact they spent so much time reverse engineering those distributions.
And so you said that you limited, I still don't quite understand, like with this redshift, you said you limited redshift, but if you take the physical distribution, you kind of, you simulate what LIGO is actually going to detect. And there is also the distribution for the redshift. Why didn't you take that distribution for the redshift? Why did you change it?
I think it's because we wanted, I think if you just, we weren't thresholding on detection. So if you used if we didn't threshold on redshift, we just have so many non-detectable, super low SNR signals.
Okay.
By putting a threshold, we changed that so the bulk of detection or signals were around the area of interest. And just out, relevant to this, our new challenge for the CW signal is even harder to get that distribution, because we don't know what's detectable very well, because we haven't detected things. So it's even harder there to tune that distribution. That's where we've got to spend a lot of our time.
Okay. Thank you very much. Thanks.
Is it fair to say, Chris, that by limiting the distance as you did was to ensure that the training samples are reliable in a sense, right? I mean, the one with the signal. Well, in the sense that they are not compatible with noise. You're not mislabeling in a sense your samples.
Yeah, we were just really scared at the beginning that imagine we had two sides to this. Imagine these people are awful, then they're not going to find any of the signals. So we have to give them some loud ones to get some. And then it's the other side. Maybe they're amazing, and maybe they get all of our signals. So we've got to give them some very low ones. And so we just had to make a distribution that covered both things and was hopefully tuned in the right area that it satisfied both sides.
Okay. There is a last hand up. This is Leila.
Hi. It was very interesting. Thank you. What I was wondering is there something, a big lesson that was learned that could be implemented for CBC searches? So is it just, no, we can use our algorithm that are tuned, or was there something like you need a front end for each type of signal? You need reverse engineering, I don't know. Is there something that, yes, that can be generalized?
So I should have had this as a slide in terms of the things taken away, specifically the CBC. Without thinking too deeply about it, one of them was whitening. Nobody really did whitening. One of the three winners did whitening, but most people didn't. They did some basic pre-processing. The winners did use just some high and low pass filtering. So that was one thing that we learned. Whitening is potentially a thing we don't need to do. The other thing was this whole front end and mapping into a spectrogram-like thing, but not a spectrogram. So some people use Q transforms, continuous wavelet transforms, or just these convolutional transforms to turn them into these 2D images. And what was the other thing I was going to say? Oh, the other thing I should have mentioned is everybody was so close. If you look at the leaderboard, we had to get Kaggle to change the number of decimal places in the metric, because everyone was so close. The top 100 was just so close with each other. So you can do almost brilliantly with very little effort with these things. That was what we learned. That they pushed for months and months, fine tuning to only get the last little bit of sensitivity. Now, if that little bit of sensitivity is actually at low false alarm rate, then that's really valuable. But we've got to dig into this still to find out that. I'm sure there's other lessons. All the challenges sort of listed some interesting things that they put in, little things into the networks, but they were all mostly with regards to getting that last fraction of the area under the curve. But to get nearly all the way, you could get away with a relatively basic approach, which is probably testament to why we were able to publish a paper in 2018 that did as well as match filtering, and we were only amateurs doing it. I don't know if that answers your question, but I need to think a bit more about the big takeaways.
No, it was a very good beginning of answer, at least I can imagine what the words of that, but at least you generalize now. Well, I think anyway, it's very interesting to use this new type of tools to make our research advance and share it broadly. Well, share even the research, not only the results.
Thank you.
Okay, I may have a very last question, and I guess we are running late now. So you said you have the forum in which you can basically follow their exchange. And is there any, so you said that the three first winners came up with the same kind of architecture, right? And this is true, right?
Similar, just in the sense of specifically defining a front end and a back end, and focusing mostly on trying to represent, pre-process the data in some sense, because they already knew it's a solved problem, classification of images. So that's why the back end is kind of standard. But the nuance in each of the way they did it was different. The second place winner, for example, did 20 separate networks.
I see.
And then had a final network to merge all of the results together. It was mad. It was just so over the top, that one.
Right. So I guess those are kind of assemble-like approach, right?
Yeah.
No, I was wondering whether the structure that they came up with is, you know, a standard solution that is known to work well, or this is the result of them, you know, running a number of options and then come up with the best one, and it happens to be the one that we saw as a result. Do you have a sense of that?
Not totally. One thing I'll say on that topic is when we make a neural network here, when we've worked on this at Glasgow, we get so picky about how many layers or how many neurons and what activation function, and they don't seem to do that. They just like, oh, I know what works for an image. It's this. I know what works for this. It's this many layers and this many neurons, and they don't stress over it too much. So there's a lot of inbuilt experience that people have that save them a lot of time in designing these things.
I see. Okay. I see hands up. Is Senwin?
Yes, that's me. I'm sorry, I just have a question. Maybe I have missed it, but you said you are going to use the real data for CGW, right? For continuous gravitation rate. But in that case, how do you evaluate it? I mean, because in the end, if it's the real data, you don't know if there's a gravitational waves or not. But how do you do that?
Yeah, I was thinking about this today. I should have worded it differently. We'd use real gravitational wave data as the noise, and then we would simulate signals on top of that noise. So it's just additive signals inside the data. So we would take the published data, assume it contains no signals because we've not found any of the continuous waves, and then we would add in software those signals.
So it would be real noise with simulated data.
Yeah,
signal,
but it did cross my mind today that if they are really, really good, and maybe there is a signal in that data we haven't found, it would be so exciting if many of them labeled something as true and we'd labeled it as false. It'd be such an interesting thing to follow up. But that's just my dream.
Yes, but I mean, I find it's very difficult to track because perhaps they found something, I mean, where we couldn't find, but I mean, I don't know. They seem a little bit tricky to do.
Yeah.
But how can they do this? Because the training sample that you would provide, you label yourself, right? You provide a label for this. So if they train their algorithm and there is indeed, you know, a signal in there because we haven't found it yet, and they train on it, how can they?
Well, because of even though O3A and O3B are very large amounts of data, we were actually limited. We could only use that as testing data. And so we're going to ask them to train. Just one of the questions that was before, there's so much data, we can't give them the correct amount of training data. We're going to have to give them the tools to generate training data.
I see, okay.
Also going to have to give them Gaussian noise and say, it's not really like that in test. And then in test, it's a mixture of Gaussian noise and real data. So it's going to be a slightly different challenge and hopefully not too hard for people, and they'll still be interested in having a go.
Well, very nice, very interesting. I think you did a very good job in conveying the difficulties of the fields and what you got from the challenge. So I think we all learned a lot from this presentation. Thank you again.
Thank you.
And well, let's close this. Yes, we cannot clap. I guess some people are clapping there. I'm not sure.